Our universe might be a single bubble in an endless cosmic foam. We are about to explore 30 incredible theories of quantum origins, from the Big Bang to the fundamental fabric of spacetime. This journey will challenge everything you think you know about reality. You will discover how the universe could have emerged from nothing, whether time is an illusion, and if our entire existence is a holographic projection. The true nature of our cosmic beginning is the ultimate mystery. What does it mean for something to come from nothing? Our story begins with the most famous cosmic origin of all, the Big Bang. Picture the entirety of our universe, every galaxy, star, and planet, compressed into a single, unimaginably hot and dense point. This is the primordial singularity, a state where the concepts of space and time as we know them simply did not exist. From this infinite condition, an explosive expansion ignited, setting the cosmos into motion. In the first fleeting moments, the universe was a searing soup of energy, rapidly cooling and condensing to form the first fundamental particles, the building blocks of everything we see today. We have tangible proof of this violent birth in the faint afterglow that permeates all of space, the cosmic microwave background radiation. It is the oldest light we can observe, a fossilized echo of that initial fireball. Yet, for all its explanatory power, the Big Bang theory contains a profound mystery at its very heart. The singularity represents a complete breakdown of our physical laws. It is a point where Einstein's theory of general relativity, which governs the very large, and quantum mechanics, which rules the very small, collide and fail. The true nature of that first moment, the spark that lit the cosmic fuse, remains one of the greatest unsolved puzzles in all of science. This initial singularity, however, left behind cosmic puzzles that the Big Bang alone could not solve. Why does the distant universe look so remarkably similar in all directions, as if every region had once been in contact? And why is the geometry of our cosmos so perfectly balanced on a knife's edge between expansion and collapse? The theory of cosmic inflation provides a stunning answer. Proposed by physicist Alan Guth, it suggests that a tiny fraction of a second after the beginning, the universe was seized by a peculiar force. Think of a single, unique quantum field, dubbed the inflaton field, that suddenly dominated everything. This field possessed a strange property, acting like a form of anti-gravity, and it caused the fabric of spacetime to stretch at an exponential, unimaginable rate. In less time than it takes to blink, a subatomic speck of the primordial universe was blown up to a size larger than our entire observable cosmos today. This incredible growth spurt ironed out any initial wrinkles, explaining the uniform temperature we see across the sky and locking the universe into the nearly flat geometry we observe. It solved the horizon and flatness problems in one elegant stroke, but inflation's most profound legacy lies in the quantum realm. Even during this period of ultra-smooth expansion, the vacuum of space was not perfectly silent. It was fizzing with tiny quantum fluctuations, minute ripples in the inflaton field itself. As the universe inflated at a breathtaking pace, these microscopic vibrations were stretched to astronomical proportions. They became the faintest imprints, the primordial blueprints for all future structure. Every galaxy, every cluster of galaxies, and the vast cosmic web we see today grew from those infinitesimal seeds. This is why cosmic inflation is a cornerstone of modern cosmology, a leading framework that connects the quantum world to the cosmic scale. Yet, for all its success, a fundamental mystery remains. We do not know what the inflaton field actually is. Identifying its true nature and how it fits into our understanding of particle physics stands as one of the most significant quests in all of science. But the idea of a single explosive beginning is not the only story. Another profound possibility is that our universe has no true start and no final end. This is the cyclic model, a vision of cosmic rebirth where the universe undergoes endless cycles of expansion and contraction. Each cycle begins with a big bang and ends in a big crunch, a violent collapse back into a hot, dense state, only to be reborn once more in a new explosion. This eternal return avoids the troubling singularity of a one-time Big Bang, replacing a single moment of creation with an infinite, rhythmic dance. The modern incarnation of this ancient idea involves a spectacular mechanism unfolding in a realm with more than the three spatial dimensions we experience. According to this theory, our entire universe is a three-dimensional membrane or brain floating within a higher dimensional space. Picture our cosmos as a single slice of an immense, multidimensional loaf of bread. The Big Bang, in this view, might not have been an explosion from a point, but a colossal collision. Our brain could have smashed into a neighboring parallel universe, an impact of unimaginable energy that flooded our space with matter and radiation, setting off the expansion we observe today. After the collision, the universes would fly apart, only to be drawn back together over eons by gravity, leading to another cataclysmic impact and a new cycle. This introduces a fascinating role for dark energy, the mysterious force accelerating the expansion of our universe. In the cyclic model, dark energy might be the crucial force that drives the brains apart after a collision, giving the newborn universe time to cool and form galaxies, stars, and planets before the next great convergence. The evidence for such a breathtaking concept is still speculative, but physicists are searching for it. The most promising place to look is the cosmic gravitational wave background, a faint, persistent rumble in the fabric of spacetime left over from the universe's most violent early moments. If the Big Bang was truly a brain collision, it would have sent powerful, unique ripples through spacetime. Finding the signature of those ripples would be like discovering the fossilized echo of a previous cosmic cycle, a whisper from a time before our own universe began. The violent collisions of cyclic models are not the only path to a multiverse. String theory, a leading candidate for a theory of everything, paints an even more expansive picture of reality. It proposes that the fundamental constituents of the universe are not point-like particles, but unimaginably tiny, vibrating strings. The different vibrational patterns of these strings give rise to all the particles and forces we observe, from electrons to gravity. A profound consequence of this theory is the requirement for extra spatial dimensions beyond the three we experience. To reconcile this with our world, theorists suggest these extra dimensions are curled up or compactified into fantastically small, complex shapes. The specific way these dimensions are folded determines the physical laws of that universe, from the strength of gravity to the mass of an electron. This is where the concept of the landscape emerges. The number of possible, stable ways to compactify these extra dimensions is not one or two, but astronomically vast. Some estimates put the number at 10 to the 500 power, a figure so large it dwarfs the number of atoms in our observable universe. Each of these configurations corresponds to a universe with a unique set of physical constants and laws. In this landscape, our cosmos is not special or fine-tuned. It is simply one possibility among an almost infinite array, a single bubble in a frothing cosmic ocean where the rules of physics are different everywhere. Our universe has the properties it does, like its curiously small cosmological constant that allows for galaxies and life, not by design but by pure chance. We exist in a pocket of the landscape where the numbers just happen to be right for us. This idea is deeply controversial as it challenges the very nature of scientific prediction. If the multiverse is real, then any conceivable set of physical laws exists somewhere. This makes the fact that our universe is life-permitting seem less like a profound mystery and more like a statistical inevitability, at least from our local perspective. The greatest challenge, however, is one of evidence. How can we ever test for the existence of other universes, forever separated from our own by an unbridgeable expanse? Some physicists search for subtle imprints left on the cosmic microwave background from ancient collisions with other bubble universes, while others hope for clues from powerful particle accelerators. For now, the string theory landscape remains a breathtaking mathematical possibility, a vision of a reality so vast it defies human intuition. This radical idea suggests that our experience of a three-dimensional world could be a magnificent illusion. The holographic principle proposes that all the information needed to describe everything within a volume of space, every star, every person, every atom, is actually encoded on its two-dimensional boundary like a cosmic hologram. The origins of this astonishing concept lie in the physics of black holes. When matter falls into a black hole, it seems to vanish forever, taking its information with it. This creates a fundamental paradox, as quantum mechanics states that information can never be truly destroyed. Physicists exploring this puzzle discovered that the maximum amount of information a region of space can contain is not proportional to its volume, as you might expect, but to the area of its surface. This is like realizing a three-dimensional box's storage capacity is determined by the surface area of its walls, not the space inside it. This bizarre finding hints that the true, fundamental degrees of freedom of the universe might live on a distant, two-dimensional surface, and our rich, three-dimensional reality is a projection from that boundary, much like a three-dimensional hologram is projected from a two-dimensional film. The implications are staggering. It challenges our most basic assumption about locality, the idea that objects are only influenced by their immediate surroundings. If reality is a projection, then two seemingly distant points in our three-dimensional world could be intimately connected on the underlying two-dimensional surface. This could provide a mechanism to resolve the black hole information paradox, suggesting the information of what falls in is not lost, but is smeared and preserved on the event horizon, the black hole's point of no return. If this is true for black holes, could it be true for our entire cosmos? Are we and everything we see just an incredibly complex holographic projection from the edges of the universe? The very nature of reality itself would be fundamentally different from what our senses perceive, a breathtaking possibility that redefines the meaning of existence. While string theory weaves a tapestry of extra dimensions, another powerful idea takes a radically different approach. Loop quantum gravity proposes that space and time are not a smooth, continuous backdrop, as Einstein described, but are instead woven from a fabric of tiny, finite loops. Imagine the void not as an empty stage, but as an incredibly fine mesh, a network of interconnected threads so small that a trillion of them could fit across a single atom. This is the spin network, the fundamental architecture of reality. In this theory, these loops are the quantized units of space itself. Area and volume come in discrete, indivisible packets, much like energy comes in quanta. This pixelation of spacetime is unimaginably fine, occurring at the minuscule Planck scale, which is why our everyday world feels perfectly smooth and continuous. This granular structure has a profound consequence for the universe's origin. If space is made of finite, quantized grains, then it cannot be crushed into an infinitely dense point. The Big Bang singularity, that moment of infinite temperature and density where our laws of physics break down, simply cannot exist in loop quantum gravity. Instead, as we rewind time, we find the universe contracts to a point of maximum possible density, a cosmic crossroads. At this moment of extreme pressure, the quantum nature of spacetime itself creates a repulsive force, a cosmic bounce. Our expanding universe, therefore, did not emerge from a singular nothingness, but from the dramatic collapse of a previous cosmic phase. This is the Big Bounce, a cyclical renewal where one universe contracts to a seed and then rebounds into a new expansion, giving our cosmos a natural beginning without a true singularity. It is a universe reborn from its own ashes, an eternal cycle of death and renewal woven into the very fabric of spacetime. Another profound leap in our understanding comes from the mind of Stephen Hawking. He and physicist James Hartle proposed a universe with no beginning at all, at least not in the way we typically imagine. This is the no-boundary proposal. It suggests that the universe is finite in time, yet has no boundary, no sharp edge where it all began. The best way to grasp this is to think of our planet Earth. You can travel across the surface of the Earth forever without ever falling off an edge. The surface is finite in area, but it is unbounded. The no-boundary proposal applies this same logic to the entirety of space-time. In this view, the moment we call the Big Bang is not a violent explosion from a point of infinite density, but more like the North Pole of the Earth. If you stand at the North Pole and ask what lies further north, the question itself becomes meaningless. There is no direction north of the North Pole. Similarly, asking what happened before the Big Bang is a question that loses its meaning in this framework. There is no before because time as we know it did not exist. To make this mathematically consistent, Hawking and Hartle introduced a fascinating concept called imaginary time. This is not time as we experience it, flowing from past to future, but a different kind of dimension that behaves more like a direction in space. In this imaginary time, the universe is perfectly smooth and rounded off like the surface of a sphere. As we approach the Big Bang in imaginary time, the universe simply closes, much like the Earth curves at the poles. This elegant idea represents a powerful attempt to marry quantum mechanics with Einstein's general relativity, providing a vision of the cosmos that is self-contained and requires no external creator or initial trigger. It describes a universe that simply is, a seamless whole where the question of a first cause evaporates into the geometry of reality itself. Yet even a self-contained universe must contend with the most fundamental question of all. Why does anything exist in the first place? One of the most daring answers comes directly from the bizarre rules of quantum mechanics. It suggests our entire cosmos could be the result of a random fluctuation emerging from a state of absolute nothingness. This idea hinges on a cornerstone of quantum theory, Heisenberg's uncertainty principle. This principle tells us that on the smallest scales, the vacuum of empty space is not truly empty. It is a seething, restless sea of potential. Certain pairs of properties, like energy and time, are locked in a quantum trade-off. We cannot precisely know both at the same instant. This inherent fuzziness means that energy does not have a single, fixed value. For incredibly brief moments, energy can seemingly appear out of nowhere, borrowed from the universe itself, as long as it is paid back almost immediately. These fleeting events are called quantum fluctuations. We see their effects in the lab, with virtual particles popping into and out of existence all the time. Now take this concept and stretch it to its ultimate limit. What if, in the beginning, there was not even a vacuum, not even space or time, but a perfect metaphysical nothing? No particles, no fields, no dimensions, no laws, a true void. In such a state, the uncertainty principle would still apply to the concepts of energy and time, or rather, to their complete absence. A quantum fluctuation could occur, but with nothing to borrow from and no time in which to repay the debt, this fluctuation could become permanent. In this scenario, the seed of the universe itself could have spontaneously appeared, a tiny bubble of spacetime containing all the energy needed for every galaxy and star. The entire cosmos would, in effect, be a single, stabilized quantum fluctuation that never vanished. This radical proposition attempts to answer the ancient philosophical question of why there is something rather than nothing by grounding it in the laws of physics. Yet it immediately confronts us with a profound challenge. What do we truly mean by nothing? Is the quantum vacuum, with its latent fields and potential for fluctuation, really nothing, or is it just a different kind of something? The theory pushes us to redefine nothingness not as empty space, but as the absence of space, time, and physical laws themselves. If our universe is such a fluctuation, then it truly did come from nothing, and the ultimate question shifts from what caused the universe to what are the fundamental principles that allow nothing to spontaneously become something. But what if our cosmic inflation never truly stopped? The stunningly rapid expansion that smoothed our early universe may be a force without end, a perpetual engine of creation. In the theory of eternal inflation, the process that forged our universe continues to spawn new ones forever. Picture the primordial inflaton field not as a uniform sheet, but as a wildly uneven landscape of hills and valleys. In most regions, the field's energy eventually drops, rolling down into a valley and converting its energy into the hot soup of particles for a new universe like our own. This is the end of inflation for that region, but due to quantum fluctuations, other patches of this field can get stuck on a high-energy plateau. In these lucky regions, the repulsive gravity of the inflaton field keeps inflation going eternally. From the perspective of one of these inflating patches, it is constantly giving birth to new, separate pocket universes that pinch off into their own distinct realities. Each of these bubbles is a full-fledged cosmos, potentially with its own unique set of physical laws and constants. The specific properties of a universe are determined by how the inflaton field settles in its final state. This final state dictates the strength of gravity, the masses of elementary particles, and even the number of spatial dimensions. Our universe appears finely tuned for life because we exist within a bubble where the numbers just happen to work out. In a cosmos with a slightly stronger nuclear force, stars would burn out in a flash. With a slightly weaker force, complex atoms might never form at all. The multiverse offers a powerful, if controversial, explanation for this apparent fine-tuning through the anthropic principle. We should not be surprised to find ourselves in a universe capable of supporting life, because in an infinite multiverse containing every possible combination of physical laws, only those rare, habitable pockets can give rise to observers who can ponder their own existence. Our universe is not a special, designed creation. It is simply one address in an immeasurably vast cosmic neighborhood where the local bylaws allow for galaxies, planets, and life. The rest of the multiverse could be a chaotic, alien place filled with universes that collapse instantly, or where matter is unstable, or where gravity is too weak to ever form a single star. We are living in a bubble of cosmic habitability, a single stable island in a frothing, infinite ocean of possibility. Another provocative possibility redefines the very nature of our existence. The simulation hypothesis suggests that our universe, with all its quantum strangeness and cosmic grandeur, is not fundamental reality. Instead, it could be an incredibly sophisticated computer simulation, an ancestor simulation run by a post-human civilization. This is not science fiction, but a serious argument put forward by philosophers and scientists, including Nick Bostrom, who breaks it down into a striking logical triad. At least one of these propositions is almost certainly true. First, that almost all civilizations like ours go extinct before reaching a post-human stage capable of such simulations. Or second, that any civilization reaching that stage has absolutely zero interest in running ancestor simulations. Or third, that we are almost certainly living in a simulation. If even a tiny fraction of advanced civilizations run vast numbers of simulations for research or entertainment, then the number of simulated minds would vastly outnumber the base reality minds. Statistically, any randomly selected conscious being, like you or me, is far more likely to be in a simulation. The quantum weirdness we observe could be a hint of this underlying digital nature. The pixelation of spacetime suggested by theories like loop quantum gravity could be the fundamental resolution of the simulation. The strange collapse of the quantum wave function, where possibilities become a single reality upon observation, could be a processing optimization, a way for the simulation to render only what is being actively measured to save computational power. Glitches in physical laws or mathematical constants could be evidence of this, though none have been definitively found. Yet, immense challenges stand against this idea. The computational power required to simulate every particle in a universe is staggering, perhaps physically impossible even for an advanced civilization. Some physicists argue that the inherent randomness and noisiness of quantum mechanics would be too computationally expensive to simulate perfectly, making our reality evidence against the hypothesis. Others point out that if we are in a simulation, the simulators could easily correct for any errors or glitches we might detect. This theory, in essence, functions as a modern creation myth, replacing a divine creator with a hyper-advanced programmer. It reframes the ultimate question of our origins, not as where the universe came from, but who or what is running the code. Roger Penrose offers a vision of cosmic eternity that challenges our deepest intuitions about time. His theory, conformal cyclic cosmology, proposes that the universe undergoes an infinite sequence of cycles, which he calls eons. Each eon begins with a big bang and ends in an unimaginably distant future. But here is the radical twist. The end of one universe and the beginning of the next are not separated by a violent crunch or a collision, but by a profound transformation of scale. In the far future of any eon, after black holes have evaporated and all matter has decayed, the universe will contain nothing but massless particles like photons, spreading out across an ever-expanding, nearly empty void. In this state, the concept of distance and time loses all meaning. There is no ruler left to measure size and no clock left to tick. A universe of pure radiation, stretched to infinite vastness, becomes mathematically identical to a universe compressed into an infinitely hot, dense point. The end, therefore, can be seamlessly conformed or rescaled to become the new beginning. The cold, empty death of one eon becomes the hot, dense birth of the next in an endless, smooth cycle. This is not a bounce but a cosmic reset, where the final state of one epoch is geometrically identical to the initial singularity of the next. To support this breathtaking idea, Penrose points to potential evidence imprinted on the oldest light we can see. He and his colleagues argue that the cosmic microwave background radiation should contain faint, circular imprints, which he calls Hawking points. These are hypothesized to be the ghostly remnants of supermassive black holes from a previous eon. According to Stephen Hawking's work, black holes slowly lose mass and eventually evaporate in a final burst of radiation. In Penrose's model, the immense energy released by the evaporation of the very last black holes in a prior eon could have left faint, circular scars on the cosmic microwave background of our own eon. Finding these patterns would be like discovering fossilized whispers from a time before our Big Bang. The scientific community remains deeply divided on this claim. Many researchers suggest the alleged Hawking points could be explained by more conventional astrophysical processes or statistical noise. Yet the search continues, for if verified, it would be our first direct glimpse beyond the horizon of our own cosmic beginning, revealing that our universe is but one link in an infinite chain of existence. A radically different path to quantum gravity builds our universe not from strings or loops, but from simple geometric shapes. The theory of causal dynamical triangulations takes the profound idea of a pixelated reality and gives it a specific, elegant form. Imagine the fundamental fabric of spacetime as a vast, dynamic Lego set where the building blocks are not cubes, but tiny, four-dimensional triangular pieces called simplices. Each simplex is a chunk of spacetime connecting to its neighbors in a specific causal way. This causal rule is the most crucial ingredient. It ensures that within the model, cause always precedes effect. Time is not an illusion here, but a fundamental, directed dimension that gives structure to the entire cosmic assembly. Researchers begin their simulations with a random, chaotic soup of these triangles, a state representing the primordial quantum foam. Then they let the rules play out, allowing the geometry to evolve according to the simple, unbreakable laws of quantum mechanics. The result is nothing short of breathtaking. From this initial chaos, a smooth, four-dimensional universe spontaneously emerges. It is not programmed in, it crystallizes on its own. This is like watching a perfectly structured ice crystal form from a turbulent, liquid chaos, governed only by the fundamental properties of water molecules. The model shows that the large-scale properties of our cosmos, its four-dimensional nature and the smooth, classical spacetime we experience, can be a natural, emergent consequence of these simple quantum gravitational building blocks. It provides a computer-simulated bridge, a step-by-step pathway showing how the fuzzy, probabilistic quantum world can give rise to the definite, classical reality we observe all around us. The universe, in this view, is not a given. It is a phase of matter, a stable structure that condenses from a more fundamental, disordered quantum state when the right conditions are met. This cosmic cycle of collisions finds another powerful expression in the ekpyrotic universe. The name itself comes from the ancient Greek word for conflagration, a great fire, and it paints a dramatic picture of our origins. In this model, our three-dimensional universe is a single membrane or brain, floating within a hidden, higher-dimensional space. Picture two immense, parallel sheets of reality, separated by a tiny gap. For most of cosmic history, these brains are empty, cold, and static, but they are slowly drawn together by an invisible force, moving on a collision course across the higher dimensions. The Big Bang, in this view, was not an explosion from a point of infinite density. It was a big splat, the moment when our brain smashed into its neighbor. The kinetic energy of that colossal impact was instantly converted into the searing heat and dense matter that filled our universe, igniting the expansion we observe today. This is a fundamentally different starting point. There is no singularity, no moment where the laws of physics break down. Instead, our universe was born from a pre-existing state, a simple, cold, empty brain that was energized by a violent encounter. After the collision, the brains bounce apart, and the universe within them expands and cools, allowing galaxies to form. Over an almost unimaginable timescale, the force drawing them together once again dominates and the cycle repeats. This ekpyrotic cycle offers an elegant alternative to cosmic inflation for solving the same cosmic puzzles. The gentle, slow approach of the brains before the collision naturally smooths and flattens our universe, explaining its large-scale uniformity without requiring a period of hyper-fast expansion. It also makes a distinct prediction about the primordial ripples in spacetime. While inflation typically generates a sea of gravitational waves, the ekpyrotic scenario produces them only very weakly. This means that if future observatories fail to detect this specific gravitational wave background in the cosmos, it would be a major point in favor of the ekpyrotic model over traditional inflation. The search for this silent signature is a direct hunt for evidence of a cosmic collision, an echo of the splat that may have created everything we know. This idea turns the cosmos into a Russian nesting doll of unimaginable scale. Black hole cosmology proposes that our entire universe might exist within a black hole, which itself resides inside a much larger parent universe. Every black hole that forms in that parent cosmos could be the seed for a new reality, a self-contained universe blossoming within its hidden depths. The formation of a black hole in the parent universe would be our Big Bang. From our perspective inside, we experience an expanding cosmos that began from a hot, dense state. But for an observer outside looking at our universe's origin, they would simply see a star collapsing, forming an event horizon, a point of no return. Our moment of creation is their moment of ultimate destruction. The singularity at the heart of our Big Bang would correspond directly to that event horizon for the outside observer. This resolves the troubling singularity, as the infinite density is merely a coordinate singularity, a limitation of our perspective from within the bubble. Inside, we see an endless expansion. Outside, it is a frozen, timeless boundary. This leads to a staggering vision of reality, a fractal multiverse. Each black hole in our universe could itself contain an entire cosmos, each with its own galaxies, stars, and planets. And each of those stars could collapse to form new black holes, birthing new universes in an endless, branching tree of existence. Our universe is not the top level, but merely one branch on an infinite cosmic tree. This also profoundly warps our understanding of time. The flow of time we experience inside our cosmic bubble is vastly different from the time in the parent universe. As matter falls toward a black hole's event horizon, time appears to slow down from an external viewpoint, nearly stopping at the boundary itself. This means the entire 14 billion-year history of our universe, from the Big Bang to this very moment, could be just a fleeting instant in the timeline of the parent cosmos. Our eons of cosmic evolution are a single blink of an eye in a higher reality. The search for evidence is a hunt for subtle fingerprints. Some physicists suggest that the pattern of primordial density fluctuations imprinted on the cosmic microwave background, the very blueprint for galaxies, might carry a signature of this ancestral structure. If our universe was born from a black hole, its initial conditions might not be perfectly smooth, but could bear the imprint of the parent star's quantum information. Finding such a pattern would be like discovering a cosmic birth certificate, a message from the universe that gave us life. This leads us to a theory that places consciousness itself at the very heart of cosmic creation. John Archibald Wheeler's participatory anthropic principle proposes a truly mind-bending idea. The universe does not exist in a definite state independent of its observers. Instead, we are participants in bringing the cosmos into being. The act of observation is what solidifies reality from a haze of quantum potential. To grasp this, we must dive into one of the most famous experiments in quantum physics, the double slit. When particles like electrons are fired one by one at a screen through two slits, they do not behave like tiny bullets. If no one is watching which slit they pass through, each particle seems to go through both slits simultaneously, creating an interference pattern on the detector screen. It exists as a wave of possibilities. The astonishing moment comes when physicists place a measuring device to observe which slit each electron actually goes through. The behavior changes instantly. The electrons begin acting like definite particles passing through one slit or the other, and the interference pattern vanishes. The very act of looking forces the particle to choose a single, concrete history. Wheeler took this bizarre quantum quirk and stretched it to a cosmic scale. He devised a thought experiment called the delayed choice experiment. What if we could postpone the decision to observe or not until long after the particle has already passed through the slits? The results are the same. The observer's choice in the present seems to determine the particle's behavior in the distant past. This suggests that the past is not fixed. It is mutable, waiting to be defined by a future observation. Now, apply this logic to the origin of everything. The initial quantum fluctuation that sparked the Big Bang was a probabilistic event, a flicker in a sea of potential. According to Wheeler's radical vision, that primordial fluctuation remained in an unresolved, ghostly state of possibility until it was finally observed by a conscious being billions of years later. Our act of looking back in time through our telescopes and our theories is what retroactively solidified the universe's own birth. We are not just living in the universe. The universe exists because we are here to see it. This idea elevates consciousness from a passive byproduct of cosmic evolution to a fundamental, active ingredient in the recipe for reality. It is a profound and deeply controversial inversion of cause and effect. We are not just reading the cosmic story. Our observation is the pen that writes its very first line. This blurring of past and future points toward an even more radical idea, that time itself is not a fundamental element of reality. The thermal time hypothesis proposes that our one-way journey from past to future is not written into the cosmos's deepest laws. Instead, it emerges from the laws of thermodynamics, from the simple, statistical tendency for things to become more disordered. The flow of time, in this view, is a consequence of the universe's overwhelming urge to increase its entropy, a measure of its disorder. We perceive an arrow of time for the same reason a cup of hot coffee left on a table always cools down to room temperature, never spontaneously heating up. It is statistically far more likely for energy to spread out than to concentrate. This directionality, this thermodynamic arrow, is what our brains interpret as the relentless march of time. But what happens when we rewind the cosmic clock all the way back to the beginning? In that primordial state, the universe was in an incredibly hot, dense, and highly ordered condition of extremely low entropy. This is the ultimate cosmic puzzle: why the universe started in such a special, finely tuned state. According to the thermal time hypothesis, as we approach this initial point, the statistical processes that generate the arrow of time break down. The distinction between cause and effect, between past and future, begins to dissolve. The universe would have transitioned from a timeless, pure quantum state where all moments were equally possible, into the thermodynamic state we now inhabit, where events unfold in a single, irreversible sequence. This suggests the Big Bang was not just the beginning of space, but the moment time itself was born from a deeper, timeless quantum geometry. Our experience of duration, of history unfolding, would be a kind of cosmic mirage, a story told by the increasing disorder of the universe. This abstract network of quantum bits offers a stunning new answer to the question of what space actually is. The theory of quantum gravity proposes that the empty void between stars and galaxies is not a fundamental stage. It is an illusion that emerges from something far more basic. Picture the entire cosmos as an unimaginably vast and dynamic social network. In the beginning, at the highest energies imaginable, every single node in this network was connected to every other node. There were no distant points because every point was a neighbor. This was a state of pure connection, a blazing, disordered soup of relationships with no concept of here or there, no before or after. Space and time, as we understand them, simply did not exist in this primordial state. It was a purely quantum geometric foam where the very ideas of location and sequence were meaningless. But as the universe expanded and cooled, this overheated network underwent a dramatic transformation, much like water freezing into ice. The countless connections began to snap, reordering themselves into a stable, regular pattern. In this great cosmic freeze, a structure crystallized. Most connections were severed, but a specific, limited number were retained, defining a local neighborhood for each point. This frozen pattern is the three-dimensional lattice of space we move through today. The distance between two objects is not a fundamental property, but simply a measure of how many of these surviving links you must traverse to get from one to the other. Your journey from your chair to the door is not through a pre-existing space. You are moving across the frozen connections of this underlying quantum graph. This phase transition from chaos to order did not happen in space and time. It created space and time. The emergence of our smooth, continuous reality from this discrete lattice explains why we see no granularity in the vacuum. The nodes of the graph are so phenomenally tiny, existing at the Planck scale, that the lattice appears perfectly smooth to all our instruments, just as a sheet of paper feels smooth despite being made of discrete fibers. If quantum gravity is correct, it means that the cosmos we call home is essentially a cosmic crystal that formed in the first moments of existence, its rigid structure giving rise to the dimensions we call length, width, depth, and duration. But what if the strange connections of the quantum world are not strange at all? They might be the most natural state of existence. Physicist David Bohm proposed a breathtakingly holistic vision of reality to explain this, an idea he called the implicate order. Bohm saw the universe as having two fundamental layers: the world we perceive with our senses, the world of separate objects and linear time, is the explicate order. This is the unfolded reality, the temporary manifestation we all navigate. But beneath this surface world lies a far deeper and more fundamental realm, the implicate order. This is the unfolded reality, a state where everything in the universe is seamlessly interconnected and woven together. Think of a simple analogy. Imagine you have a drop of ink and you slowly stir it into a viscous liquid like glycerin. As you stir, the ink seems to disappear, becoming enfolded into the liquid. No part of the ink is truly gone. It has simply been distributed throughout the whole. If you then stir in reverse, the ink droplet will miraculously re-emerge, perfectly formed, unfolding back into the explicate order. In Bohm's view, every particle, every force, every moment of our reality is like that ink droplet. It is an unfolded projection from this vast, interconnected implicate whole. The entire universe, from the quantum foam to the cosmic web, is a continuous unfolding from this deeper level. This provides a powerful framework for understanding quantum weirdness, the phenomenon of entanglement where two particles remain instantly connected across vast distances is no longer a paradox. In the implicate order, those particles were never truly separate to begin with. Their apparent separation in our explicate world is an illusion, like two different patterns emerging from the same underlying liquid. Their connection is immediate because at the fundamental level they are still one. This view also completely redefines our understanding of time. In the implicate order, past, present, and future are all enfolded together. Time as a linear sequence is not a fundamental feature of reality, but a derived concept that emerges as things unfold into our observable world. The entire history of the cosmos, from the Big Bang to its final state, exists simultaneously in this enfolded totality. Our conscious experience of moving through time is just our local journey through this eternal, unfolding process. The quantum origin of the universe, then, was not an explosion in a void, but a moment of profound unfolding, a ripple moving from the implicate into the explicate. Our search for the beginning of time is a search within a reality that has already transcended it, a quest to understand the first note of a song that was always playing in its entirety. This matrix model of M-theory presents a universe born from a state of pure information. Imagine our cosmos not starting as a point in space, but as a mathematical object, a vast square grid of numbers. This is not a physical structure in any dimension we would recognize. It is a zero-dimensional quantum matrix, a dense network of interactions where the very concepts of here and there have no meaning. Within this primordial matrix, the fundamental ingredients are not particles or forces, but simple zeros and ones, quantum bits interacting according to the elegant rules of their underlying algebra. The dynamics of this system are everything. As these quantum numbers interact and evolve, they do not exist in a spacetime. Their interactions create spacetime. The model describes a phase transition, a sudden and dramatic shift in the state of the entire matrix, akin to water freezing into ice. In that critical moment, the chaotic, interconnected web of the matrix spontaneously crystallizes. A specific, stable pattern emerges from the quantum noise. This pattern is our four-dimensional reality. Three of the matrix's internal degrees of freedom unfurl to become the familiar dimensions of length, width, and depth. A fourth degree of freedom becomes the one-way arrow of time. The Big Bang in this radical picture was not a violent explosion from a singularity. It was this geometric awakening, the moment the matrix quantum code generated the very stage of space and time upon which our cosmic drama would play out. This provides a profoundly non-singular beginning. There is no point of infinite density where the laws of physics break down because there was no pre-existing space for it to occupy. Instead, the origin was a computational transition, a shift from a zero-dimensional state of pure potential into a universe with definite dimensions and a clear history. The force of gravity itself, and perhaps all the fundamental forces, would not be primary entities but emergent phenomena. They would be the effective descriptions of how this underlying matrix behaves on the large scales we can observe, much like the fluidity of water emerges from the collective motion of countless molecules. We are left to wonder if the constants of nature, the precise numbers that allow for stars and life, are simply the frozen-in parameters of that initial matrix transition, the unique solution to a cosmic equation that had to solve itself. The smooth, continuous expanse of our cosmos could be a magnificent illusion. Causal set theory proposes that spacetime is not a fluid fabric, but is instead built from a vast collection of discrete, indivisible elements. Think of these as the atoms of spacetime itself, the fundamental grains from which reality is woven. These atoms are not scattered randomly, they are organized by a single, powerful principle, causality. Each atom is linked to others in a network of cause and effect. One event, one atom, comes before another in a strict, partial order. From this incredibly sparse foundation, the entire richness of our four-dimensional universe emerges. The theory suggests that the smooth, curved spacetime described by Einstein's general relativity is not fundamental. It is a large-scale, approximate description of this underlying causal network, much like the smooth surface of a lake emerges from the chaotic motion of countless water molecules. The crucial insight is that the volume of space is not a primary concept. In causal set theory, the number of these spacetime atoms in a region directly defines its volume. This beautifully simple idea has a profound consequence for the origin of everything. If the universe is a growing causal set, then it must have started with a first event, a single, primordial atom of spacetime. This first cause had no past, no predecessor. From that solitary beginning, new atoms were born, linked by new causal relationships, growing the network that would become our cosmos. This growth provides a natural, non-singular beginning to the universe, completely avoiding the infinities of the classical Big Bang. There was no point of infinite density because there was no continuous space to be infinitely dense. There was only the first element in a chain of causality that would eventually blossom into the universe we inhabit today. The theory even offers a potential explanation for the arrow of time. The relentless growth of the causal set, the continual addition of new atoms, provides a fundamental directionality that our macroscopic experience of time might ultimately derive from. We are not moving through time, we are witnessing the ongoing creation of the cosmic network itself. Lawrence Krauss offers a provocative answer to the ancient question of existence, framing the universe's origin not as a miracle but as a cosmic free lunch. He builds on the work of James Hartle and Stephen Hawking, focusing on a specific scientific definition of nothing. This is not the philosophical void of absolute non-being, but the quantum vacuum of empty space. In our universe, even the most perfect vacuum is not truly empty. It is a seething, restless sea of virtual particles, constantly popping into and out of existence in fleeting pairs, borrowing energy from the universe for the briefest of moments before annihilating and paying back the debt. These virtual particle pairs are not just theoretical. We see their effects in laboratory experiments, and they are essential for our understanding of how atoms and light interact. Now Krauss asks us to take this concept to its ultimate conclusion. What if we apply the rules of quantum mechanics not just to particles within space, but to the fabric of spacetime itself? In this view, the quantum vacuum is fundamentally unstable. It is a state that is constantly fluctuating, and given enough time, or rather, given the inherent fuzziness of quantum time, a fluctuation of monumental proportions can occur. The entire universe could be the ultimate quantum fluctuation, a bubble of spacetime that simply appeared. The most compelling part of this idea is the concept of zero total energy. For the universe to come from nothing, it must have a net energy of zero. This seems impossible when we look at all the stars and galaxies, but gravity holds the key. Gravity has negative energy. The positive energy bound up in all the matter and radiation in the cosmos is perfectly balanced by the negative gravitational energy of all that mass pulling on itself. Think of it like building a tower. It takes a great deal of positive energy to lift all the materials against Earth's gravity. That stored positive energy is exactly cancelled out by the increased negative gravitational potential energy you now have. The universe in its totality is that tower. It is a vast, complex structure whose total energy sums precisely to zero. This means the universe requires no external source of energy to exist. It could have spontaneously emerged from the unstable quantum vacuum, a fluctuation that borrowed zero energy and therefore never had to be paid back. The cosmos is the ultimate free lunch, a stunningly complex something that, when all accounts are settled, costs absolutely nothing. The instability of nothing, governed by the known laws of physics, makes the existence of our universe not only possible but perhaps statistically inevitable over immense, perhaps infinite durations. This radical proposition reframes the ultimate question, suggesting we should not ask why there is something rather than nothing, but why the laws of physics are such that nothing is inherently unstable, forever tending to become something. This observer-centric view pushes quantum mechanics to its most profound and controversial extreme. A universe that requires a witness to bring it into being challenges the very core of scientific realism, the idea that a physical world exists independently of us. The physicist Eugene Wigner sharpened this paradox with a famous thought experiment. He imagined a friend in a laboratory performing the classic double-slit experiment. From Wigner's perspective outside the lab, the entire system, including his friend and the particle, remains in a blurred superposition of states until he himself opens the door and asks for the result. At that moment, his observation collapses not just the particle's state, but the memory and experience of his friend as well. This suggests that consciousness itself is the ultimate agent that resolves quantum uncertainty, transforming shimmering potential into concrete fact. If this is true, then the birth of our cosmos presents a monumental chicken and egg problem. The Big Bang in this radical interpretation was not merely a physical event. It was the first quantum measurement. Before that moment, all possible universes existed in a tangled superposition, a silent fog of every conceivable physical law and cosmic history. For this primordial haze of possibilities to crystallize into the single, specific universe we observe, a form of measurement had to occur. But what could have performed that first observation? There was no human, no instrument, no complex life. This line of reasoning forces us to consider a staggering possibility. Did the universe require a primordial, foundational form of consciousness to be born? This idea ignites a fierce philosophical battle between realism and idealism. Realism holds that reality exists on its own, while idealism argues that reality is fundamentally mental or conscious. The observer-created universe leans heavily toward idealism, proposing that mind is not a late-coming accident in a material world, but a primary ingredient woven into the fabric of existence from the very first moment. Perhaps the universe awoke itself. Maybe the initial conditions contained a proto-conscious quality, a self-awareness that allowed it to observe its own birth and, in doing so, choose its own reality from an infinite menu of possibilities. This is not to suggest a divine being in a traditional sense, but a universe that is inherently aware, a cosmos whose very existence is an act of self-observation. The implications ripple through every moment of our lives. Your own conscious awareness right now is not just a passive receiver of a predetermined world. It is an active participant in a continuous act of creation, collaboratively sustaining the reality you take for granted. Are we living in a universe that dreamed itself into being, and are we the very means by which it continues to dream? The holographic principle transforms the Big Bang from a violent explosion into an information processing event. Our four-dimensional universe of space and time may have been projected into existence from a two-dimensional boundary, like a cosmic movie being played from a celestial film reel. In this radical view, the initial singularity, that point of infinite density where our laws of physics break down, is not the true beginning. It is merely a shadow, a flawed perspective from within the projection. The real action was happening on the lower dimensional surface that contains the universe's complete description. The moment we call the Big Bang was simply the instant this cosmic projector switched on. The physics governing this boundary surface does not involve a singularity. It is a realm of quantum fields and information theory where everything remains well-behaved and finite. The terrifying question of what happened before the Big Bang is reframed. It becomes a question of what computations were running on the boundary before the projection began. This holographic origin story elegantly sidesteps the problem of the initial singularity by moving the ultimate cause outside of our observable spacetime. The fundamental laws are not those of gravity and particles in a four-dimensional theater, but the rules of quantum bits and entanglement on the two-dimensional screen. The universe's birth becomes a translation, a transfer of information from a simpler, lower-dimensional reality into the rich, complex world we experience. Your own existence, the stars in the night sky, the very fabric of reality, could be the result of an unimaginably complex data processing event unfolding on the distant edge of everything. Our physical reality might be a collective hallucination. The chair you are sitting on feels solid, the ground beneath your feet seems firm, and the space between stars appears vast and empty. Yet, a revolutionary idea in theoretical physics suggests that space, time, and even gravity are not fundamental ingredients of the cosmos. They are emergent phenomena, collective behaviors that arise from a deeper, more basic layer of reality that lacks these very properties. Think of temperature. You can feel that a cup of coffee is hot, but that sensation does not come from a single, fundamental substance called heat. It emerges from the frantic, collective motion of trillions of water molecules. Temperature is a useful, large-scale description of an underlying microscopic reality. In the exact same way, the emergent universe theory proposes that the smooth, continuous stage of spacetime is not the final word. It is a useful illusion that crystallizes from a more fundamental, non-spatiotemporal system. This underlying reality could be a vast quantum computer, a dense network of entangled quantum bits, or a purely informational structure where the concepts of here, there, before, and after have no meaning. In this primordial state, there are no distances to measure and no clocks to tick. There is only a web of pure quantum relationships. The Big Bang, then, was not an explosion in space and time, but the moment this underlying network underwent a dramatic phase transition. It organized itself, freezing into the stable, geometric structure we now recognize as our four-dimensional cosmos. This is how gravity itself could emerge. Einstein described gravity as the curvature of spacetime, but in this view, that curvature is not primary. It is a statistical consequence, a large-scale average of the frenetic activity in the quantum substrate below, much like the calm surface of a lake emerges from the chaotic motion of countless water molecules. This perspective unites several approaches to quantum gravity, from holography to loop quantum gravity, under one powerful theme. It suggests our universe originated not from a singular point, but from a state of pure, organized information, a cosmic code that, when executed, generated the reality we call home. The universe's arrow of time may not be a one-way street, but one lane of a cosmic two-way road. This is the theory of the biverse, a pair of universes born together from a single, symmetrical origin. One of these universes is our own, expanding forward in time from the Big Bang. The other is its perfect mirror, a twin universe evolving backward in time from that very same point. They are not separate creations, but two halves of a single, profound whole, linked by a fundamental principle of physics known as CPT symmetry. This symmetry states that if you reverse the charge of every particle, flip its spatial parity as if in a mirror, and reverse the direction of time, the laws of physics should remain perfectly unchanged. The biverse theory applies this ultimate symmetry to the cosmos itself. At the moment of the Big Bang, this perfect CPT symmetric state was realized, giving birth to two universes that are mirror images in charge, parity, and the flow of time. Our universe, with its matter and forward-flowing time, is balanced by an anti-universe made predominantly of antimatter and evolving backward in time from the beginning. This elegant duality provides a stunningly simple solution to one of cosmology's deepest mysteries, the problem of low initial entropy. Why did our universe begin in such an incredibly ordered, low-entropy state, a condition so special it set the entire arrow of time in motion? In the biverse model, the question is turned on its head. The Big Bang was not the beginning of a single, low-entropy universe. It was the moment of maximum order and symmetry for the entire biverse system. From that perfectly ordered midpoint, both universes evolved away, increasing in entropy as they moved in opposite temporal directions. For us, time flows forward into disorder. For our twin, their time flows backward into their own future, which is also a state of increasing disorder from their perspective. This explains why we remember the past but not the future. Our past is the low-entropy state of the Big Bang. Our future is the high-entropy state of cosmic heat death. Our memories are records of that increasing disorder. In the anti-universe, observers would have the opposite experience. They would remember what we call the future and find our past to be unknown to them. We are not flowing toward an end, but away from a mutual beginning. This symmetric origin story removes the need for a special, finely tuned initial condition, painting our one-way experience of time as a local perspective within a grander, two-sided cosmic structure. The quantum world is a realm of shimmering possibilities, but we live in a world of concrete facts. How does this transition from the many to the one actually happen? Quantum Darwinism offers a compelling answer, and its logic might just explain the very architecture of our universe. This theory proposes that classical reality emerges through a process of selection. In any quantum system, countless potential states exist simultaneously. But when this system interacts with its environment, with photons of light, stray atoms, or any other particle-specific states get imprinted onto that environment. They are copied over and over again like a message being broadcast. The states that are the most robust, the ones that can be most effectively recorded and duplicated by the surroundings, are the ones we end up perceiving. They are selected to become our objective reality, while the other fragile possibilities simply fade away. Now, cast this idea back to the universe's first moments. The primordial vacuum was a quantum foam fizzing with every conceivable fluctuation. An infinite number of potential universes were vying for existence, each with slightly different properties. But then, inflation began. The universe's environment began to expand at an exponential, staggering rate. This explosive growth acted as the ultimate copying machine. Only the most stable, most resilient quantum fluctuations could be effectively imprinted onto this rapidly stretching fabric of spacetime. They were the ones successfully recorded, their patterns multiplied across the entire sky. These were the fluctuations selected by the cosmic environment to survive. All the other potentialities, the universes that were too unstable or irregular, were simply washed away by the inflationary deluge, leaving no lasting record. The specific imprints that endured are the ones we now detect as the faint temperature variations in the cosmic microwave background. These are the blueprints that gravity would later use to sculpt every galaxy, star, and planet. In this view, the large-scale structure of our cosmos isn't random. It is the result of a primordial natural selection, where the quantum fluctuations best suited to being copied by an inflating environment were the ones chosen to become classical reality. We live in a universe that was selected for its ability to be observed, its fundamental patterns forged in the first moments by a cosmic version of the survival of the fittest. Stephen Hawking's final cosmological vision turns our understanding of cause and effect completely upside down. He proposed that the universe does not possess one single, fixed history, unfolding from a definite beginning to an uncertain future. Instead, our past is malleable, shaped in a top-down fashion by the very fact of our existence in the present. This radical idea rests on a cornerstone of quantum mechanics known as the sum over history's approach. In the quantum world, a particle traveling from point A to point B does not take one single path. It simultaneously explores every possible route, every conceivable trajectory, no matter how unlikely. The reality we observe is the weighted average of all these histories. Hawking and his collaborator Thomas Hertog applied this logic to the entire cosmos. They suggested that there is no one unique story of the Big Bang and its aftermath. There is a vast superposition of every possible universe, each with its own initial conditions and physical laws. So how does one specific cosmic history, our history, become real? The answer lies in the final state, in the conditions of the present that act as a filter. Our existence here and now, in a universe that has galaxies, stars, planets, and life, effectively selects the past that could have led to us. We see a certain cosmic history, not because it was predetermined at the beginning, but because it is the only kind of history compatible with the observers we are today. Imagine a vast, tangled tree of possibilities, with countless branches representing every way a universe could have begun and evolved. We are not looking back along a single, solid trunk. We are perched on one specific leaf, and from our vantage point, we trace a single, consistent path back down to the roots. That path is our past, but it is not the only past that exists in the quantum haze of probabilities. The universe's origin is not a fixed starting line. It is a consequence. In this top-down cosmology, the Big Bang itself is retroactively defined by the fact that billions of years later, conscious beings would emerge to look back and ask how it all began. The question of why the universe has the specific properties that allow for life is answered with a profound circularity. It has those properties because we are here to see them, and our presence selects the history that made us possible. This dissolves the need for a finely tuned initial singularity, replacing it with a cosmic democracy of possibilities where our present reality casts a vote for its own creation. Dark energy may have been the universe's first and most powerful force. We know it today as the mysterious presence accelerating the expansion of the cosmos, but its influence could reach back to the very dawn of time. Some physicists propose that what we call dark energy is the modern remnant of the very field that drove cosmic inflation. In those first fleeting moments, this field, sometimes called quintessence, possessed an incredible repulsive gravity. It acted like a form of anti-gravity, causing the fabric of spacetime to stretch at an exponential, unimaginable rate. This was not the gentle acceleration we see today, but a violent, all-encompassing repulsion that forged the cosmos in an instant. The transition from that initial quantum state to the classical universe we inhabit might have been triggered by a shift in this dark energy field. Picture a ball resting on the peak of a steep hill, representing the high energy state that powered inflation. The universe was unstable, poised for change. With a tiny quantum nudge, the ball rolled down into the valley below. As it settled, the energy of the field was released, flooding the universe with the hot soup of particles and radiation that would become everything we see. The repulsive gravity vanished, and the more familiar force of attraction took over, allowing matter to clump and form galaxies. This intimate link between dark energy and inflation suggests that the beginning of the universe is inextricably tied to its ultimate fate. The same force that set the cosmos in motion is now gently pushing it apart, guiding it toward a distant, cold, and empty end. Understanding the true nature of dark energy is not just about predicting our future, but about uncovering the very first moment of our past. Why did this field exist, and why did it have the precise properties needed to create a universe capable of harboring life? The answer might lie in the deepest laws of quantum gravity waiting to be found. The universe may have begun not with a bang, but with a calculation. This theory frames the cosmos as the output of a quantum computer of unimaginable scale, where the Big Bang was the moment this system booted up. In this view, the fundamental stuff of reality is not energy or matter, but quantum information. Every particle, every force, every ripple in spacetime is ultimately a pattern of bits, zeros, and ones existing in a superposition of states. The laws of physics we have painstakingly uncovered are not fundamental rules etched into the cosmos. They are the algorithms, the software protocols that govern how this quantum information processes and evolves. Gravity, electromagnetism, even the passage of time itself, emerge from the relentless, logical execution of this underlying code. Think of a stunningly realistic video game. The world you see on the screen appears to have mountains, rivers, and solid objects obeying physical laws. But at its core, it is all just information being processed according to the game's programming. Our universe could be a vastly more complex version of this, running on a quantum substrate where every possible outcome is computed simultaneously. This provides a powerful new perspective on the puzzle of quantum entanglement. When two particles are entangled, their fates are linked instantly across any distance. In the quantum computer model, this is not spooky action at a distance. It is a simple matter of data correlation. The particles will never separate data points to begin with. They are part of a single, unified computation, and measuring one simply updates the shared information state, a process that is immediate because it is logical, not physical. The very fabric of spacetime could be a network of entangled quantum bits. The distance between two stars would not be a fundamental void, but a measure of the computational complexity required to relate the information at one location to the information at the other. In this breathtaking vision, the cosmos did not explode into being. It processed itself into existence, computing the very stage of space and time upon which we now stand. A final theory of everything would not point to a beginning, but to a timeless necessity. This ultimate framework seeks to unite gravity with quantum mechanics, not to find a starting gun for the cosmos, but to reveal a reality so logically coherent that it could not have been otherwise. Such a theory would describe a self-contained system, a perfect set of mathematical relations where every piece locks into place. In this vision, asking what caused the universe becomes as meaningless as asking what causes the rules of arithmetic. 2 plus 2 equals 4 not because of an initial event, but because the entire system of mathematics demands it. The universe in its entirety might be the same kind of brute fact. Our profound need for a first cause could be a deep-seated illusion, a cognitive limitation born from our existence within time. We are creatures of sequence, hardwired to see a chain of events where there might only be an eternal, unchanging truth. The laws of physics would not be a set of instructions for how the universe behaves. They would be the universe, its very essence. There is no separate clockwork and clock. The mechanism and the ticking are one and the same. If this is true, then the quantum origin was not a moment in time. It is a fundamental feature of a reality that simply is, always was, and always will be in a state of necessary existence. Our entire journey from the Big Bang to the multiverse then becomes a beautiful exploration not of how everything started, but of why this particular, self-consistent reality is the only one possible. The ultimate answer to the mystery of existence might be that there is no mystery at all, only a truth so elegant and complete that it needs no external explanation. We have traveled from the explosive birth of the Big Bang to the silent geometry of a timeless reality. This journey through 30 cosmic origin stories reveals a truth more profound than any single answer. Our quest to understand the universe's first moment is not just a scientific pursuit. It is a fundamental human adventure, a grand exploration that stretches the limits of our knowledge, challenges our deepest philosophies, and ignites our collective imagination. We have seen universes born from collisions in higher dimensions, from quantum fluctuations in an absolute void, and from the sheer necessity of mathematical consistency. We have considered the possibility that our entire cosmos is a simulation, a hologram, or a single bubble in an infinite multiverse. Each theory, from the established framework of inflation to the speculative reaches of the implicate order, offers a unique window into the greatest mystery of all. This ongoing search reminds us that science is a living, breathing story, constantly rewritten with every new discovery and every bold idea. The cosmos does not give up its secrets easily, but the act of seeking itself expands our understanding of what is possible. So we turn this final question over to you. After this incredible journey through the quantum dawn of everything, which vision of our origins speaks to you the most? Do you find yourself drawn to the cyclic rebirth of the ekpyrotic universe, the participatory magic of an observer-created reality, or the stark elegance of a cosmos from nothing? Share your favorite theory in the comments below. Let us know what captivates your imagination. If you enjoyed this deep dive into the foundations of reality, subscribe for more journeys to the edge of our understanding. And always keep looking up at the star-filled sky, forever wondering what secrets it holds.